Yeah, great. Okay, thank you very much, Donna. That was an incredibly hard act to follow because it was a fantastic talk, and literally because you've given me no time to speak. It's really, I just want to say it's such a pleasure to be all in person. I'm like literally vibrating because of all the coffee coursing through my veins. The unique sort of conference thing, and also everyone's wearing real trousers. Okay, so I'm going to talk about two different extensional systems, the main Ethiopian rift system and also the Eastern North American margin, and thanks to Donna for setting those up so nicely. And essentially the takeaway message here is the more we look, the more complicated things get, but I think that's very much within the theme of what we've seen so far. Of course, all the best and most important work done here is by my graduate students, Brennan Brunswick and John Petraska, and I also want to acknowledge Colton Lina on the whole ENAM stuff. Okay, so without further ado, for a quick outline. So I will talk about sort of how wide is narrow, the case of Ethiopia, and I'll show you two recent studies that we've been involved in, imaging the lithospheric structure from roof to flank with, I think, unprecedented detail, and then also show you some new velocity and attenuation tomography, and then think about how static is passive, the case of ENAM with some new velocity and anisotropy tomography. And here's some nice pictures for you to look at when I say this thing. Okay, so for about 3 decades, of course, we've had this sort of dichotomy that's been set up between weak and because it's hot and therefore wide rifting versus strong lithosphere, which undergoes, which is cold, and therefore the rifting is relatively narrow. And that's sort of fairly well established, but there are some recent models that maybe challenge this idea, and there are some dynamical models that actually suggest that things might sort of go the other way, where as you increase the molar temperatures, you make the whole plate hotter because of the effects that has on the strength of the crust. That might actually focus the rifting processes, and you get narrower and narrower rifts as you get hotter and hotter, which is interesting. And you can see I put the East African rift on there. East African rift, as everyone in this room knows, is one of the most studied places on the planet, and I'm going to miss out 95% of the incredible studies that have been done here. I wanted to draw your attention to the fact that previously a lot of the focus in terms of where the broadband deployments have sort of focused themselves is on the rift axis, and only relatively recently have we sort of extended our broadband coverage all the way out to the extreme rift flank to the border of Ethiopia. And so this has led to some new findings, including some of those which are here today. I wanted to also pull up the work of Emma Chambers and her co-authors who have used ambient noise surface waves to show that yes, the rift itself is particularly slow, but actually the slow regions extend significantly towards Lake Tana. You can see that also from the radial anisotropy. And this sort of plays somewhat interestingly with previous sort of at this point almost canonical studies of this rift system that show, yes, there is some crustal thinning within the rift axis, but actually the way that that penetrates off the rift axis is a little bit uneven. In the north, not so much. In the south, pervasively thin crust. And then also some people would say that there's a clear demarcation between on rift, where the lithosphere has been completely degraded, and off rift, where you still see a strong mantle lithosphere, versus other people that say that actually there's sort of this very wide zone of low velocities. I will note that this is very similar to some things that I'll show you in a couple more slides, but until we've had this deployment right off onto the rift flank, we've not really been able to pin down the westernmost extent of these low velocities. Okay, so this is a strange angle. It's not the same as on your Zoom screen. We're going to use this. Okay, so we used almost 2 decades of broadband seismic data from all the deployments shown in here. And in particular, I just want to highlight these new stations deployed between 2014 and 16 in an effort led by Katie Keranen. And so we sort of thrown all these together, and we're measuring radio wave phase delays and inverting those using electron tomography for phase velocities. And you can see sort of the coverage of our rays and of our earthquakes, and it's good. And so to cut to the chase, this is sort of what we see. These are the new maps of surface wave phase velocities all the way from the rift center to the extreme rift flank. Right, so this is, we sort of extended this coverage. And because I don't have very long, I'll just focus on some of the most important things you see here. Low velocities within the rift axis, that's good. Then we go away from the rift axis and things get faster. That's also sort of what we expect. And then you keep going away from the rift axis, and in the shallow parts of this model, I'm showing you here periods. The rule of thumb is you take the period and multiply it by 1.5, and you get depth-ish. right? As we go further away from the rift axis, things get slower again, okay? And that's evident in the shorter periods, the shallow parts of the model, but in the deeper parts, that's actually not really seen, right? We still see low velocities that are broadening beneath the rift axis. So we took the surface wave phase velocities, and then also calculated using a new receiver function quality control and clustering algorithm developed by collaborators at Brown University, led by Hannah Kruger, and sort of constructed a new database of receiver functions from all the new stations deployed as part of this effort, and you can see that they look quite nice. And then we take these two data sets together because they're very complementary. You've seen this sort of thing before. The receiver functions are sensitive to velocity gradients, but no absolute velocity control. The surface wave phase velocities have sensitivity to absolute velocity, but poor vertical resolution. So we sort of ally these things together and jointly invert them in some fancy algorithm that's transdimensional Bayesian inversion that we come up with ensembles of models that fit all of these data together. So here are some of those slices through the models. So you're seeing a bunch of velocities at all the stations that we did the inversion at, and here we focused on the off-rift, the kind of flank regions. On the top left, you can see crosstalk thicknesses, and these are in pretty good agreement with what other people have seen without the benefit of the joint inversion of the surface wave, so that's still encouraging. And in short, you can see that there's relatively thin crust away from where the flood basalts and underplating have really thickened the Ethiopian plateau. And as you get into the plateau, things don't look simple in any sort of straightforward way, right? We have some regions of thinner crust extending to the rift axis, and these are sort of actually similar to the locations of a couple of important volcanic lineaments. And some of the thickest crust is up here in the north, in the region of this little icon here, which is Lake Tana, which is the largest lake in Ethiopia, as many of you know. And then looking at the velocities, you can see that it's a little bit of a grab bag, but I want to isolate a couple of features. And in order to sort of simplify these things to just the most important features, what we did was take all of the shear velocity profiles and throw them into a clustering algorithm that asks, how many groups do we need, and what are the most similar shear velocity groups? So we tried this with 2 groups and 3 groups and 4 groups, and it turned out that 3 groups gave us the best balance of intra-group similarity and parsimony. And so here are the 3 groups. So group 1 comprises basically the off-rift regions in the flank, but not all of those regions, because there is this lineament where you can see these slow velocities corresponding to group 2, which are away from the rift axis in this sort of sub-parallel lineament, but there's a clear separation between those and the rift axis. And then group 3 is sort of everything else, which is closer to the rift where things are systemically slow. So we can take these 3 and we can sort of look at them and compare them to some regional analogs. The first point I want to make is that even though I'll refer to a faster group and slower groups, they're all slow, right? These are all very, very slow compared to something like Prem, which is this gray dashed line. There's the fastest group, the blue one, is slow compared to a regional analog, which is kind of the Mozambique belt to the south. But nevertheless, we can make some. So they're all slow, we can make some interpretations. So the blue group represents the stations that sit on structure where there's still sort of a lithosphere that has a relatively fast lid with a gradual lithosphere boundary that we're seeing for the first time. The green group is very similar to the blue group, with the exception, because you can see they sort of come together at the bottom, but in the uppermost mantle lithosphere, the green group is statistically significantly slower. And then finally, the red group sort of represents the ridge, and you can see that not only does it agree with various previous studies, but it's actually slower than the globally average 0 to 25 million-year-old oceans. And that's kind of interesting how bloody slow it is. Partly that could be because there are limited melt infiltration pathways, so there's sort of more melt stuck in the upper mantle here. So we take these 3 groups, and then of course what we want to know is, well, how do these actually correspond to the physical conditions of the mantle in this location? So we did this in a couple of ways, and I'm only showing you the stupid and simple way here because it's a little bit easier to explain. What we did was say, well, we know that these are slow, and what could cause this slowness? Well, the primary drivers we think are lower temperatures and adding in melt. And we have a bunch of parameterizations for how those 2 things change our velocities. So we say, let's imagine that Prem represents boring ambient mantle with a mantle potential temperature of 1300 degrees that is melt-free. And then we can add slowness to that by elevating temperatures or by adding in melt. right? And so we construct these sort of slowness contours in slowness space. And there's a perfect trade-off between those. And then we can take the ensemble from our groups, so we can plot them up onto this slowness space, and we can see sort of the error bands. But of course, melt and temperature cannot freely trade off with each other, right? Thermodynamics says that as you increase temperature, you also produce some melt. So we calculated using few melts what a melting curve would look like. And of course, if there are petrologists in the room, they're probably cringing inside. They're like, oh, you put in the wrong things, and then if you put in water, it's all different. And of course, this is a vast simplification, and this is very uncertain relationships. But I would argue that it's not sort of unconstrained. So you can put in your own, right? We gave you this little figure. You can put in your own melting curves, whatever you want, and you will get some overlap between these groups with their own internal uncertainties, and between these curves and their uncertainties. And that circumscribes the region of temperature and melt fractional space that sort of obtains beneath these regions. So assuming that this is not a sort of a terrible formulation here, we can see that the blue group requires elevated temperatures, but not necessarily any melt. The red group, as we sort of expect, that's on the rift, we have highest temperatures and a substantial amount of melt. What's interesting is this green group, which is way off on the rift axis, sorry, on the rift flank, has elevated temperatures and up to something like 0.7% melt in the uppermost lithosphere. Okay, so what am I doing? Okay. Okay, so that was the surface wave study. I also wanted to show you some new imaging done with body wave tomography, which I think is quite complementary. So here is all the stations that I used. We measure differential travel times, 12 and change thousand the travel times, thousands of Ps, thousands of S, from almost 2 decades worth of deployments in this region. You can see those travel times plotted on here. Blue means fast, early arriving body waves, red means slow, late arriving body waves. And we invert these for structure using differential velocity tomography, using finite frequency kernels to project the sensitivity of these travel times down into the earth with 1D ray tracing and other bells and whistles. And I just want to show you both the P wave differential travel times and the S wave differential travel times, because if you just look at the data, it's very, very obvious that this is not a simple narrow rift, right, which we've known for a while. But I think for the first time, we're really capturing the northwesternmost extent of the low velocity region in a way that I think we haven't really seen before, even though it's obviously been hinted at in previous data. So we take these and invert them for structure. And here are on the left, the P wave, and on the right, the S wave models. And I'm happy to look at my laptop and show you these at leisure later, but don't have much time, except to say that the rift axis is obviously very slow. And then there's a severe asymmetry between immediately transitioning to very fast velocities to the southeast of the rift and having this really protracted region of low velocity, particularly in the north, and particularly along this sort of lineament extending southwest from Lake Tana. You see that in the P waves. Oops. And you see maybe even better in the S waves, right, where you can see that there is actually sort of a fast region between these two lineaments, right, and that's seen in other data types, and then it gets slower again further away from the axis. Because we have these two, first I'm going to show you some cross sections through these models. Here's a horizontal slice that you were seeing before, and here are a couple of cross sections in the north and in the south, and I've labeled on here the horizontal extent of the main Ethiopian rift axis as demarcated by those border faults. And you can see that if I didn't put that on there, you'd have no idea where the rift is, right? You certainly wouldn't know that it's all the way on that side, I think. Again, these show this very sharp transition off to the southeast of the rift and a much broader transition to the northwest that extends with these low velocities kind of reaching up towards Lake Tana here. This is the P waves. I wouldn't believe the vertical extents of all of these anomalies once you get below 300 and change kilometers, just because the aperture of the individual arrays, if not the entire array involved, but you can believe things sort of above this, and that was the Q waves, and this is the S waves, and this sort of shows this even more clearly. Here you would definitely know that the slowest velocities are beneath the rift axis, but there are very slow velocities off axis as well, but they don't necessarily extend down to great depth, right? That seems like it's a shallow upper lithosphere mantle sort of feature. Because we have these two independent constraints, we can actually, I can actually show you the excess relative VS to VP reduction. And what this basically means is red colors are places where shear velocity is depressed more than you would expect compared to compressional velocity, and we would infer that that means that there's melt in the system. And indeed, you can see that down the rift axis, we see these regions of red where there's probably melt in there. But importantly, there's this kind of bullseye beneath Lake Tana. It extends down to the south-southwest from there. And there is sort of connections across this region that actually align with some of the superficial volcanic lineaments. Okay, so some of the geophysics says that this drift is super broad at depth. What about right at the surface? So if we take GPS velocities, and Sarah, somewhere here in the audience, you should ask her about these, right? On the right-hand side is her recent model, and the left-hand side some other models. You can see that even though there is, you can argue that there is somewhat broad distribution of extension measured at the surface, right? We're still looking at something between 200 to 200, so maybe 400 kilometers of extent, and it's sort of mostly focused on the rift axis, right? This doesn't look like the 600 and change horizontal extent that we're seeing at depth. Moreover, I sort of view, as I said to Sarah in the restaurant yesterday, I sort of view this figure as absence of evidence being evidence of absence, right? Sarah didn't need to fit the GPS velocities over 600 kilometers of extent in order to satisfy all of the observational constraints. She could do it with a relatively narrow feature. So, so that's kind of interesting. There are all sorts of asymmetries in even the shallow data extending all the way to the rift axis. If you actually look in detail at how the individual rift segments are extending, they seem to be bracketed most often by much harder backstops to the east side than to the west side, and there's asymmetry in individual segments. There's asymmetry in various other sort of geophysical observations, including the elastic thickness, which is asymmetric, although not nearly as asymmetric as those low velocities, which I showed you. And there's also, to an extent, more seismicity in the western, this is a relatively recent compilation, more seismicity in the western parts of the plateau, and it kind of shuts off pretty quickly going into the Somalian plateau. But it doesn't look like the same as what we're seeing at depth. What time am I supposed to? Okay, so so this is very much work in progress. I'm showing this in the spirit of open collaboration and wanting your feedback. So this was the body wave differential travel time measurements, and now I'm showing you body wave differential attenuation measurements. And you, I think, will agree with me that they're not nearly as simple to interpret, but they have the potential to really tell us a huge amount about what we're seeing in the system, because attenuation provides a different and complementary constraint on the physical mechanisms behind body wave heterogeneity, behind, are we seeing temperature, we see melt, we see other effects, fluids, etc. So if I take these measurements and I invert them all together, so we have 9,000 differential T-star measurements, lots of P, lots of S, from, again, 20 years worth of data. And these measurements are made in a way using this comb of filters approach, which I developed, which fits both amplitudes and phase differential amplitude and differential phase spectra in a way that is supposed to filter out the effects of focusing. And if we invert these using finite frequency kernels that are properly scaled to 1D Q structure with 1D ray tracing, and I'm going to throw all 9,000 of these together into a single model, because I think that the measurements are very messy, and so it's, I just want the simpler structure. So I get to do that by assuming that all of the deviation in attenuation is in shear and none of it's in bulk. You can argue with me later. And so that allows me to fix the two together. And these are the models that I get. And frankly, I don't fully understand these models that I get. And I've done this in other places like Alaska, and they look great, right? They're really easy to interpret. So I'm not convinced that it's just that I've messed up, although I'd be receptive to that feedback, right? So some things make sense, right? Some things you can see that there is high values of attenuation, and in particular, those seem to follow the sort of western boundary of the FR, just like the lowest velocities. There's also these high values of attenuation off the rift axis in the region that we saw low velocities as well. But if you look down the rift axis, especially in locations where, and if I show you these locations where the volcanoes are, you can see I've plotted on volcanic centers. There's pretty low attenuation. In fact, there's sort of lower than average attenuation, which really is very mysterious to me, right? So if I sort of plot on from the velocity tomography where I think some of the lithospheric sort of rough LED boundaries are, you can see maybe that these regions of high attenuation sort of bracket some of the edges of the what might be LAB topography, and this sort of brought up to me the wonderful work of Ben Holtzman and his co-authors in sort of imagining that LAB topography really drives and channels lots of the most active parts of these systems and shutting down. Okay, well, we won't talk about so it's possible that these are locations where there's actually melt that is being sort of focused at the LAB. But I'm extremely dissatisfied with the question marks here. So this slide, as it says, is a cry for help, right? If you have ideas, right, I would be really, really grateful for your thoughts on this. I'll move very quickly through the slides. Don't got longer. Okay, I will not. I mean, it's like a whole other study here. So what I do want to show, because I think it's important, is you should go and read this paper by my grad students. I feel like I'm getting played off the stage. In a nutshell, what we did was conduct joint azimuthal anisotropy and velocity tomography using simultaneously measured splitting measurements and differential travel time measurements. And you can invert those together in a way that resolves the trade-offs that are present in the anisotropic parts of the velocity model. And on top, I'm showing you velocities, and red colors are slow, blue colors are fast. On the bottom, you're seeing azimuthal anisotropy, where blue colors are fast parallel to the Eastern North American margin, and red colors are fast perpendicular to the margin, so parallel to paleo spreading. And this is just sort of, this played off. So this is just sort of the absolute punchlines of what we're seeing here. And you can see that going into this is a cross section that you can see through here, going down sort of to the southeast through the Eilon CSE region. And you can see, we see the continental interior. We see these really low velocities associated with the Harrisonburg anomaly. And then we see those actually extend to depth in a way that hasn't been really imaged, in my view, all that well before. And one of the possibilities that this brings up is that what we're seeing here is edge-driven convection, driven by the contrast in the temperatures at the continental margin. It's also possible, and this is argued for, I think, quite persuasively by Eilon and her authors in figures they didn't have time to show, that there's a component of shear-driven upwelling here, which is as we're moving the continent, which has LAB topography on it, over the convecting mantle, that instigates an element of upwelling. The trouble is, these numerical models suggest that these two processes are in competition. And it's very difficult to have one be strong and also have the other be strong. It's a little bit of an either or. In the anisotropy, the things that I wanted to point out are that we see actually layered anisotropy in this region. And importantly, we see, I think for the first time, that in the lithosphere, and here you can see the Appalachians, and here that's the shoreline, and we extend offshore using EOBS stations. We can see actually there's an extension parallel fabric in the lithosphere here. But below that, we see a different fabric, right, which is margin parallel mantle flow. And I think this sort of tells us about some of the density-driven models that are sort of acceptable candidates for what's going on here, because lots of density-driven models in this region don't necessarily show this, but we're imaging it very strongly, and so I think that is a robust feature. And I guess I'll leave you with that.
Okay, we're going to go on to our last speaker in this session, Noah Phillip, and lunch is at noon. So